Okay, welcome back Mathcounts friends. In today's video, I've got the third installment of my new Foundation series of Mathcounts videos. I intended to put this one out yesterday, but ended up with a flat tire. So this is what happened to me yesterday as I was driving someone back home from our church Christmas party, and got that all taken care of today, so I'm good to go. I decided that today might be a good day to talk about plane geometry. We do have the school competition coming up tomorrow, so this video will probably be too late for any of you unless you stay up late to benefit from this for the school competition, but this will be useful in the future. So here we go. All right, let's jump right in. I'm going to go through a bunch of problems, and as in the last video, they will get harder as we go along. So I'll start with this one, which is pretty easy. This one says, what is the side length of an equilateral triangle with perimeter of 48 millimeters? Okay, so we've got an equilateral triangle, and the important thing here is to realize that since it's equilateral, all the sides are the same length, okay? And so the perimeter here is just going to be 3 times the side length. All right, so we can have all the side lengths be the same. We'll just call them x. The perimeter will be 3x, and that's equal to 48. We're given that here. Also, I've got some Christmas music my wife's playing in the background, so hopefully that's not too distracting, but maybe it'll be really nice. I like it. Let's see. What is the side length of the equilateral triangle? Okay, so they want to know the side length, so that's x, so we just divide both sides by 3, and we get 16. All right, so that's our final answer on this one. Okay, not too bad. Let's take a look at this one. So this one says use the figure shown at right. Oh yeah, so this was one of the 2 problems where we were going to use this figure. So don't have to worry about these numbers here, but segment BC is parallel to EF. Okay, so these are parallel, and it says the points BE and A are collinear. Okay, that's a straight line here, as are the points AFC, so a straight line here. It says if AE is 4, let's put that here, and BE is 4, and AC is 12. Okay, so this is 12 all the way from here down to here. How long is segment AF? Okay, so let's put our X there because that's the one that we want to know. It's this distance from here down to here, X. Okay, so the nice thing is that because these 2 lines are parallel, we can know that these 2 angles are the same, okay? Because this is a straight line. So because those 2 angles are the same, and obviously, well, it means we've got 2 similar triangles. So we've got triangle AEF, that's the little one up the top, is going to be similar to triangle ABC, which is the whole thing, right? So these are similar because they have this as a shared angle, and this is also, it's not the same as these 2, but it's the same angle in these 2 triangles because it's a shared angle. So maybe I should do it in a different color since it's not the same as those 2. So this angle here, so you've got a green and pink angle on both of these triangles, so those 2 triangles are similar. All right, so because they're similar, we can use ratios. Our last video was about ratios. We can use the ratio of this full length to this partial length, okay? So that's the length of this side on the big triangle to this side on the smaller triangle. So that's 8 divided by 4. And that's going to be equal to the corresponding sides of this, this other side. So we've got 12 for the big triangle here, and then x. So it's going to be 12 divided by x. And if we multiply both sides by 4x, or in other words, cross multiply, we get 48 is equal to 8x. And that means x is equal to 6. So that's our answer on that one. All right, again, please pause the videos and you know, when you see the problem, and try to work it out on your own before you view the solution. This one says, in isosceles triangle LMN, okay, so let's see, I should draw an isosceles triangle, I guess. In isosceles triangle MN, well, let's draw it like that, I guess, because we've got a, that probably doesn't look quite like a 68 degrees, but they say only angle L measures 68 degrees. So let's put 68 here. And then M and N, we don't know what those are yet. Oops, a little too many wiggles in my M. M and N. What is the degree measure of angle M? Okay, so this is what they want to know. So there's two things we need for this. We need to know that in an isosceles triangle, two of the angles are the same. And we know that it can't be M and L that are the same because L is the only one that's 68 degrees. And by the same logic, it can't be N and L. So that means it has to be M and N that are the same. So we can put an X here. The other thing you have to know is that the three interior angles of a triangle add up to 180 degrees. So now we have 180 degrees plus, or no, 180 degrees equals, 180 degrees equals 68 plus X. I can just put that as 2X. And if we subtract 68 from each side, let's see, we got 112, I should say, 112, right? And that's equal to 2X. So when you divide both sides by 2, we'll get X equals 56. And that's our answer there, just 56. Okay, let's take this next one. This one says, what is the supplement of the complement of an angle that measures 75 degrees? Okay, so this is pretty confusing wording here. Let's break it down. They want to know the supplement of the complement of an angle that measures 75 degrees. So let's maybe start here. What's the complement of 75 degrees? So what is a complement first? A complement is the angle, if you have an angle X here, the complement is the angle that you have to add to it, this Y angle here, in order to get to 90 degrees. Okay, so we could think like if X was 75, the complement over here would be 15, but we don't actually need to figure that out because they want the complement of the complement. The complement of an angle is just the angle itself. So they're just trying to confuse you here. The complement of 75 is just 75. And then they want to know the supplement of that. So really all we need to know is what is the supplement of 75. And what is the supplement? So the supplement is the angle. Let's take our 75 again here. That probably should have been a little bigger. The supplement is the one, this is the supplement here. It's the one that you have to add in order to fill out the full 180 degrees. So here we were filling out the full 90 degrees. Here we're filling out the full 180 degrees. So we can just take 180 minus 75. So yeah, it's just a matter of remembering which one's bigger, the supplement or the complement. One is 90 degrees, one is 180 degrees, and I usually think about it as S being bigger than C because alphabetically it comes later in the alphabet. That's just the way I remember it. But the supplement is the one that, when added, gets you to 180. So here we got 180 minus 75. That'll give us 105 degrees for our final answer on this one. Okay. This one says, in equilateral triangle XYZ shown, YZ is 3x plus 1, XZ is 4x minus 7, and if all the lengths are given in feet, what is XY? Okay, so let's put Y here. That's what we want to find. A lot of times we use X for what we want to find, but they've already used X over here, so I'm going to put Y here instead. So that is interesting. They didn't give us any lengths at all, but they told us that it's an equilateral triangle, and that's the key, because that means that all these lengths are the same. So we could say Y is equal to 3x plus 1, which is also equal to 4x minus 7. And if we just look at this part here, we can figure out what x is. So to do that, let's subtract x, or let's subtract 3x from both sides. That'll give us 1 here is equal to x minus 7. Okay, so that means x is going to be 8. And now we can plug that into either one of these two. Let's just try this one since it's right there, in order to get y. And we should get the same thing, whether we plug it into 3x plus 1 or 4x minus 7. That's maybe a way to double check our work. But 3x plus 1 will be 24 plus 1, so y will be 25. Okay, and let's just try it on the other one too. 4x minus 7, so that'll be 32 for 4x. You subtract 7, you also get 25. So it worked. Okay, good. So 25 is our final answer on that one. All right, let's move on to this one. This one says, in the figure, point C lies on segment AE, point D lies on segment BF, and segments AB, CD, and EF are parallel. Okay, so let's make a note of that. Let's make a note that these are all parallel. Okay, and if the ratios of CD to EF, okay, CD to EF, that's these two, and AC to CE both equal 3/5. So okay, so if this is X here, this will be 3/5 of X here. That's what it means for these to have the ratio of 3/5. And AC to CE, okay, so if this is Y here, then this will be 3/5 of Y here, just from A to C. What is the ratio of the area of trapezoid ABDC to the area of ABFE? So that's the area of the top one to the area of the whole thing. Okay, so yeah, so that's going to be a little bit tricky now, isn't it? So the first thing we need to do is figure out maybe how long AB is, because in order to find the area of this top trapezoid, we're going to need to know both of the bases. We already know the base CD is 3/5 of X, but we don't know the AB distance yet. Maybe I should draw this again so that we have a little more room. I know it's pretty cramped up there. So let's redraw this. And we've got 3/5 Y here. We've got Y here. We've got 3/5 of X here. And we've got X here. And all these are parallel. Okay, so that's what we start with. And now we need to figure out this length here from A to B. This is A to B. Okay, so there's some ratios we can use here, because basically if you look at it, there's a certain amount of, you could make a right angle here, and you could make a right angle here, and by using that we can figure out something about these two segments. Let me draw these two segments in gold here. So this segment here and this segment here. Okay, and we can do the same thing on the other side as well, and we'll get a segment here and a segment here. You know, if we draw that, no, that's not quite right. Let me draw those vertical lines for a second. So we're going to draw this one down here and then this one down here. So the gold segment on this side will be here. So the sum of these two segments is the difference between 3/5 X and X. So the sum of those two, maybe I'll just call this, well, I don't want to use A. Let's call this W and Z or something. So W plus Z is equal to the difference between these two lengths. So that'll be 2/5 of X. And the sum of these two, I'm going to call this one W prime and this one Z prime, because there's going to be a relationship between those two. W prime plus Z prime is going to be equal to something, right? That's going to be the difference between 3/5 X and this thing that we're looking for. And what I'd like to convince you guys of is that using these similar triangles over here, we know that this sum is going to have to be 3/5 of this sum. Okay, so this sum was 2/5, and because this length here, this 3/5 Y, is 3/5 as long as this Y here, that means these similar triangles here, and also these ones here, are going to be able to be used to relate this W prime and Z prime to W and Z. And so W prime plus Z prime is going to be 3/5 of the 2/5 of X. So what is that? That should be 6/25. 6/25 of X. And then this AB distance is going to be 3/5 of x minus the 6/25. So let's see. 3/5 is 15/25. I'm subtracting 6/25, so this should be 9/25 of x up here. Okay, very good. So now I can compute, at least in terms of x and y, something, well, okay, I can't actually compute it directly in terms of x and y because I don't know this height, but the area of this top trapezoid is going to be related to this height h here, right? Which I also don't know, but it's, but we can write it at least in terms of x and h. And you know what? I'm not going to call this one h. I think I'm going to call this one h instead, and I'm going to call this one, I'm going to call that one 3/5 of h, because I can get that from the similar triangles here, where I have 3/5 of y and y. So this one's going to be 3/5. I'm sorry, this is so small. I should have drawn this bigger. So this height of this triangle is h, and this height of this triangle, and also the trapezoid, is 3/5 of h. So now we can figure out the area of the top triangle in terms of x and h. So we're going to have the average of the two bases. That's going to be 3/5. So I'm going to write it as 15/25. 15/25 plus 9/25. Those are the two bases. And I need to take the average of those, or 1/2 the sum of those. That's going to be like that's going to be the average width of this trapezoid. It's also the width of like the middle part. And in order to find the area of a trapezoid, you need to multiply that by the height. So we multiply that. That I forgot to write the x in there, so that should be multiplied by x. And then I need to, did I say add? I need to multiply. I'm going to write the multiply just as a dot. So I need to multiply this by 3/5 of h. I can simplify things a little bit here, especially because 15 plus 9, well, let's see, that'll be 24/25. So half of that will be 12/25. So I have 12/25 of x times 3/5 of h. That's the area of my little trapezoid, okay? So maybe I'll just write that as 36 over 125 xh. Okay, now I can compute the area of the big trapezoid. So the area of the big trapezoid will be the average of x and 9/25 of x. So that's 25 plus 9. That'll give me 34. We divide by 2, that'll be 17/25 as the average. 17/25 x times the height. And the height is h plus 3/5 of h, which is 8/5 of h. Okay, so this is the area of the big trapezoid. This is the area of the little trapezoid. And what did they want to know? They wanted to know the ratio of the area of the small one to the area of the big one. So we need to take this as our numerator and this as our denominator and find that ratio. The x and the h are going to cancel out. We can do that here. And the 125 is going to cancel out with this 25 and this 5. And now we just have 36 divided by 8 times 17. 36 divided by 8 times 17. All right, and we can take a 4 out. This becomes 9, and this becomes 2. And now we just have 9 divided by 34. So that's our final answer on this one. That was probably an easier way, to be honest. I should have probably worked through this before. But anyway, we got the answer, 9 out of 34. All right, this one says, a rectangle has area 392 inches squared, and its length is twice its width. Okay, so let's draw a rectangle. Let's try to make its length twice its width. That looks about right to me. So we'll just call this one 2 width, and this one width. How about that? So its length is twice its width. What is the perimeter of the rectangle? Okay, so the area is going to be 2w squared which is equal to 392. And if we divide by 2 and take the square root, we get w on its own. It's going to be equal to the square root of, what's 392 divided by 2? Well, it should be 196. And yeah, so then 196 is a perfect square. So w is just going to be 14, because 14 times 14 is 196. Okay, great. Now it wants to know the perimeter. So the perimeter is just going to be 2w, that's going to be the two widths, plus 4w, right? That'll be the two longer sides. So that's just equal to 6w, and w is 14, so we just need to do 14 times 6, and that's just going to give us 84. So our answer here, whoops, our answer is 84 on this one. Okay, very nice. Let's go ahead and move on to the next one. This is problem the 8th one we have here. It's getting a little harder now. This one says, Annie's house is located at the intersection of Oak and Broad Streets. Okay, so there's Annie's house. Maybe I should use the pink instead. There's Annie's house up there. Cindy's house is at the intersection of Broad Street and Seton Lane. That's down here. So we've got the A for Annie and the C for Cindy. And it says there are two routes Annie can take from home to Cindy's house. Either she can travel 1.5 miles south on Oak Street. Okay, that means this is the 1.5. And then continue east along Seton Lane for 2 miles. That's 2 miles there. Or she can go directly to Cindy's house along Broad Street. Okay, so let's draw it over here. We've got 1.5 and 2. Or she can go this way. This is the shortcut way. Along Broad Street. It says how much shorter is the direct route along Broad Street? Okay, so one thing you have to know is that these streets are at a right angle. You can assume that because it says south and east, or does it say anything explicitly? Well, it says, yeah, it says she travels south on Oak Street and then east along Seton Lane. So that means those are perpendicular to each other. And if you happen to know your Pythagorean triples, you might recognize these numbers. This is half of 3 and this is half of 4. So this is kind of like a 3, 4, 5 triangle, right? Except it's just cut in half. So this one is cut in half to 1.5. This one's cut in half to 2. So this distance, x, is going to be half of the 5, which is equal to 2.5. And they want to know how much shorter it is to go this 2.5 miles here versus going this 3.5 miles, which is the sum of 2 and 1.5. So this total distance is 3.5. The direct route is 2.5. So how much shorter is the direct route? And the answer is that it is 1 mile shorter. And I want to point out to you that here it says miles. Normally we don't say 1 miles. But the answer here is, in fact, 1. And so I just want to point this out to you because sometimes you might see miles and think, oh, it must not be 1 because they put miles here. But in Mathcounts problems, you can't assume that. They put the units here pluralized regardless of whether it's 1 or not. So here the answer is 1 miles. And that's just the way Mathcounts does it because they don't want you to make any assumptions based on whether this is plural or not. They don't want to give away the answer by putting mile here. Right? Sometimes you can use some hints from the problem, like when they say express the answer in terms of pi, then you might say, oh, I bet the answer is some multiple of pi, or put your answer in as a fraction in simplest terms, then it's probably a fraction answer. But in this case, you can't assume that it's non-singular. The answer is non-singular based on this having an S at the end of miles. So I just wanted to point that out. All right, let's go to problem number 9 here. It says in circle O, let's draw a circle here. Oh, looks pretty good. In circle O, the lengths of chords AB and BC, okay, so AB, let's say this is AB, and BC are equal, okay. BC, these are equal. And the measure of angle ABC is 90 degrees. Okay, I can put a right angle sign there. Given that circle O has radius of 3 meters, okay, so from the center, if we go out like this, it's 3 meters. What is the length of arc ABC? Okay, so they want to know the length of this arc. Let me draw that in another color. They want to know the length of this arc from A through B all the way around to C. Whoops. I want to know the length of that arc. And it says express your answer in terms of pi. So there you go. There's that hint that we're probably going to have an answer in terms of pi. Now the key to being able to solve this problem is to know that whenever you have a right angle inscribed in a circle, the opposing side is going to be a diameter of the circle. So the hypotenuse of this right triangle, any right triangle that's inscribed in a circle, meaning that all three of its vertices are on the circle, the hypotenuse will always be a diameter. So because it's a diameter, we know that its length is twice the radius. We're going to have a radius of 3 here and a radius of 3 here, so the total length there is going to be 6. But what do we want to know? We want to know the length of the arc ABC. So the other thing we know is that because this is a diameter is that this angle between these two lines here is 180 degrees, which means that this thing that I drew in this pinkish color is actually a semicircle. It's half of the circumference of the circle. Normally we say the circumference is 2 times pi times the radius. Here we want half of the circumference, so we don't need the 2. We can just say our arc length is going to be pi times the radius. And that's kind of cool. It's if the radius is 1, the arc length is equal to just the angle here. Well, if you do the angle in radians, 180 degrees is pi radians. You guys probably don't use radians very much, but when you start using radians, that's kind of why they use that, because it makes the arc length equal to the angle, at least when you have a radius of 1. So this is going to be 3 pi now, because the radius is 3. So that's our answer here, and it is in terms of pi. Okay, what is the degree measure of each interior angle of a regular decagon? Okay, so I don't know if I can draw a decagon. Well, I'll draw something. So 1, 2, 3, 4, 5, 6. Yeah, let's see. That was not good. 1, 2. Yeah, it's not going to work. But there's 10 sides on this thing. I'll just draw a circle. There's 10 sides, so maybe I can draw the points. But anyway, you've got a decagon, and it's a regular decagon, meaning all the angles are the same, so we've got straight lines. Now, it shouldn't be a circle. These are straight lines. I'll just draw part of it. And they want to know what the interior angle is. So that's this angle here. And actually, the easier thing, when you have a regular polygon, the easier angle to compute is the exterior angle out here. Because for any regular polygon, the exterior angle is going to be equal to 360 divided by the number of sides. And the way I like to think about that is, like, let's say you're starting right here at one of the points, and you start going along the direction of one of the edges. Well, you're going to have to turn a certain amount to get going along the next edge. And then that amount that you turn is the exterior angle. And then you're going to have to turn another angle to get to the next edge. And you're going to have to do that n times. And since it's a regular polygon, all those turns are all going to be the same amount, right? So you're going to turn by a certain amount. Each time you go from one edge to the next, it's going to be the same angle. So x, 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 x. And by the time you do 10 turns, which is n, which is the number of sides, you're going to be facing the same direction you started, but you will have turned around a full time, which is 360 degrees. So the exterior angle of a regular decagon will be 360 divided by 10. So that will just be, since our number of sides n is 10, this will just be 36. But it's not asking us for the exterior angle, it's asking us for the interior angle. So to get that, you have to find the supplement. In other words, you have to take 180 minus 36, okay? And that's going to be 144. So that's our final answer, is going to be 144. Now there is another way to do this problem, which I will show you also, which maybe is a little bit more tricky, but basically when you have a regular decagon, you can think about breaking it up into a bunch of triangles. So for example, you could take all the lines from one point to all the other points except for its neighbors. So these different diagonals like this, that will break up this decagon into some number of triangles, right? And the number of triangles will be the number of points, not including itself or its neighbors, which is 7. So there's 7 of these yellow lines that you're going to draw, and plus 1, right? Because there's a triangle out here, and then there's 7 barriers, another triangle. So it's going to be 8 triangles. And each of those triangles, the sum of the interior angles is 180 degrees. So the sum of all the interior angles of the decagon is the sum of all of those, which is going to be 8 times 180. So if you want to do this in general for a polygon, it's n minus 2. The number of sides minus 2 times 180 will give you the sum of all the interior angles. And then since we have a regular one, we're going to divide by 10. So this 180 and 10 will make 18. So it's 18 times n minus 2. And n is 10, so this is 18 times 8. And that gives you the 144. Same answer we got before. So that's another way to do it. I happen to think this one's a little bit easier, but they're both pretty good. All right, let's go on to this one. This one says a particular circle has an area of 81 pi square meters. Okay, so let's draw a circle. All right. And the area is 81 pi. And it says, what is the largest square that can be inscribed in the circle? Okay, so we've got, I'm not going to use the straight line tool. You'll just have to bear with my drawing. This is supposed to be a square. Pretty close. So this is the largest square that you can inscribe in the circle. In fact, every square that you inscribe in the circle has the same area because the only way to, yeah, but anyway, what is the area of the largest square that can be inscribed in the circle? Okay, so let's draw a center for our square and our circle, and let's draw a radius that goes out here. And what is this radius going to be? Well, we know the area is 81 pi, but that is also equal to pi r squared. And so if 81 pi is the same as pi r squared, r has to be 9. So this distance is 9. And there are different ways to solve it from here, some of which involve the square root of 2. But there's a way that doesn't involve the square root of 2, which I want to show you. And that is that you can rearrange these 4 triangles into a pattern that looks a little bit like this. 2 squares that are each diagonal. This looks like I have a sandwich maker that has this pattern that I can make grilled cheese sandwiches with. But what I'll point out here is that these 4 triangles over here, right? 1, 2, 3, 4. They are like this triangle here, meaning the shorter side. Well, they've all got 90 degrees angles here. And then they've got a hypotenuse over here, and they're right isosceles triangles. So yeah, this distance is 9 root 2, but I'm trying to solve the problem without even knowing that. Basically, you can say that once you put them together into this rectangle, the height of this rectangle will be 9, and the width of this rectangle will be 18. So the area of these 4 triangles put together, which is the same as the area of this square, which is the same as the area of this rectangle, is just going to be 9 times 18, which is 81 times 2, which is 162. So that's our final answer there. The other way to do it, well, I guess the other way actually doesn't involve square root of 2 either. You could just find the area of this triangle as being 9 times 9 divided by 2, and then multiply that by 4. Actually, that's a pretty good way to do it too. You would just have 81 over 2 times 4, and that'll just be 81 times 2, which will be 162. So that's a good way too. All right, great. This one says circles A, B, and C are constructed so that each circle intersects a side of an equilateral triangle ABC at the midpoint of the side, as shown. If the perimeter of the triangle is ABC is 24, what is the area of the shaded region in the interior of the triangle? Okay, let's see if I can draw this. So I've got an equilateral triangle. Well, it doesn't say it's equilateral, but I'm pretty sure it is because let's see if I can draw these circles. Actually, that's going to be pretty tricky, isn't it? To get these circles right. I should have drawn the circles first. Yeah, okay, maybe I won't draw the circles, but I'll draw part of the circles just the part that we care about. Oops, that's not it. I have to go like this. So I'll draw this, and I'll draw this, and it's not perfect, but it'll be fine. So there's a center of one circle here at A. There's a center of a circle here at C. There's a center of a circle here at B. And we want to know the area of this shaded region here. Is that right? Yeah. Okay. So the area of that shaded region can be computed as the area of the triangle minus 3 times, well, minus the area of these 3 pi segments, right? So the 3 times area of the segment. Well, we'll say this little, I should say sector. So let me highlight that in blue here. This is the area of one sector here, right here. So we can compute both of those. Let's give it a shot here. So the area of the triangle, we need to know the base and the height. So it said the perimeter of the triangle is 24. That means that, well, yeah, I'm going to say that they're all equal. I'm going to say that it's an equilateral triangle because, oh, actually, no, it says it's an equilateral triangle, doesn't it? Okay, so that makes it really easy. So then these sides are each 8. These sides are each 8. And that means the base is 8. The height, we have to use this 30, 60, 90 triangle. So that's 30 degrees. This is 60 degrees. This is 90 degrees. And whenever you have a 30, 60, 90 triangle, like this, 30, 60, 90, this, they'll be in the ratio of square root of 3 to 2 to 1. This is a special right triangle. So in our case, instead of 1, we have 4 along here. So that means this height will be 4 times the square root of 3. Okay, so the height is 4 times the square root of 3. And so the area of the triangle, AT, is going to be 1/2 the base times the height. So that's 1/2, the base is 8, and the height is 4 root 3. So altogether, this is going to be 16 square root of 3. Now, what about these sectors? One thing I will point out is that these 3 sectors together form a semicircle. You could take this one and move it over here, for example, right? It would be over here. And then if you take this one and flip it upside down, it would go here. And now you have a semicircle. And the radius of that semicircle is 4. So the area of the semicircle, I should probably use a different letter because I don't want to confuse with AS. I'll just use an S for the semicircle area. That's going to be equal to pi r squared divided by 2, right? Pi r squared divided by 2 because it's half of the circle. And r is 4, so this is going to be equal to 8 pi because we've got 16 pi over 2. So our final area is going to be 16 square root of 3 minus 8 pi. And that's the final answer. That's just the best form we can put it in. We don't need to do anything else to it to simplify it. That's as good as we can do, unless we have a calculator. Oh, you know what? This was a calculator problem because it says express your answer as a decimal to the nearest tenth. But we're going to ignore that. We're just going to leave our answer in this form because, yeah, that's just what we're doing here. I don't have a calculator, so. All right. 2 circles are inscribed in an equilateral triangle as shown. Okay. Maybe I'm going to learn my lesson and draw my circles first. Let's see how that works. These might still be hard to get this to line up, but something like that. We'll see if we get something close to an equilateral triangle out of this. Okay, something like that. Not perfect, but good enough. All right. 2 circles are inscribed in an equilateral triangle as shown. What is the ratio of the areas of the shaded regions K to P? Okay, so the K region is up here. This region is K. And the P region is down here. This region here. That's P. Okay, so we want to know the ratio of those 2 areas. We don't have to actually compute what the areas are, maybe. So one thing you can notice is that these shapes are similar to each other because they both have 60-degree angles. Since this is an equilateral triangle, let me grab another color here. They both have 60-degree angles here. And then, you know, they just go up until they meet the circle and then they come back. So these are similar shapes here. And so if we can find the ratio, for example, between this x here and this y here, the area ratio will just be the square of that distance ratio. That's true whenever you have a 2D shape that is similar to another 2D shape. If you can find a corresponding linear dimension and you can find the ratio of those dimensions, then the area will have a ratio that's the square of that. So I guess we don't get any numbers on this problem, but we can just maybe label using some variables. We can label some things. So let's do that. Let's take the center of this circle and draw it out here and draw a radius here. And let's call that R. Maybe I'll call it big R, capital R, because there's going to be another radius on that smaller circle, and we'll call that one little r. How about that? Little r. And one thing I'd like to point out is that there is, let's see, there's a similar triangle here, isn't there? There's a triangle here with little r. Yeah, that goes like that. And then there's another one with the big R that goes like that. And another thing that I would like to point out is that even though it doesn't look like it in my drawing, the distance from this point up here down to here, let's call this A to B, that is actually the same as the distance from B to C here. Because just imagine this little circle wasn't here. This would just be a circle inscribed in an equilateral triangle. It does tell us it's an equilateral triangle. So, so yeah, this will be the same distance from B to C as from A to B, because you could take this figure and rotate it 60 degrees or flip it or whatever you want to do, and it'll be the same. So really, if we can find the ratio here between these two radiuses, that will be the ratio between this distance. Well, let me give you another point here. Let's call this one D. So the ratio of R to R, little r to big R, will be equal to, because of similar triangles here, the distance from A to D as compared to the distance from A to B. And since that A to B is the same as B to C, we can also say that that is A to D over B to C. Okay. So, and that is in fact what we were looking for. This x here is equal to the A to D, and the y here is equal to the B to C, because that distance is the same as this one also, and this distance is the same as this one. So, can we figure out the ratio of those two radiuses? So, let's see. I think we can draw a line across, tangent to both these circles, across like this. And now this point here at the center of the small circle has got some distance. Well, it's a distance r from it to the let's give this point a name here. This point here, let's just call it E, I guess. We were up to E. So from the center here to E is going to be R. So we've got R, let me just draw it in there. That's R. And then there's another R up to this point, right? There's another R there. And there's actually another R here. And let me tell you why that is. The reason is because if you see this small triangle here. That's a 30, 60, 90 triangle. And whenever you have a 30, 60, 90 triangle like that, or this is my 90-degree angle, this is my 60-degree angle, this is my 30-degree angle. So 60, 30. This distance here, which we knew was r, right, from here, that's going to be half of this distance. So this has to be 2r. And we already covered 1 to get to the top of the circle, right? So that top part up there is going to be another r. So we've got 3r from here down to here. And then we can do the same thing for this bigger 30, 60, 90 triangle to make the argument that this distance, let me draw it in gold here, this distance from A all the way to the center of the bigger circle is got to be 2 big R, 2 big R. And we know that there's 1 R here, and then these 3R, the 3 little r up here has got to be equal to a big R. So now we know that 3 little r is equal to a big R. And that's the key, because now this R over R is just equal to 1/3. And we say that's equal to AD over BC, which is this x over y. And so the ratio of the areas is going to be that thing squared. So they want to know the ratio of the areas of shaded region K to P. That's the smaller one to the bigger one. So that is going to be 1 over 9 because we square the 1 over 3. And we just make sure we pay attention to which one they want, the ratio of which one to which one. They said K to P. That's the smaller one to the bigger one. If they wanted P to K, it would have been 9. Okay, let's go on to another one. They're getting a little harder. I've got like 5 more to go here. If you stay to the end, you're amazing. Okay. In equilateral triangle ABC, M is the midpoint of side AB. Oh, I need another equilateral triangle, don't I? Okay. So I need another equilateral triangle. That's somewhat equilateral, I guess. And it says AM, or M is the midpoint of AB. So let's call this AB. And then that makes this one C, and they say M is the midpoint of AB. So it's M. If CMN, what's N? If CMN is also an equilateral triangle. Oh, okay. So we don't know where N is, but it says that CMN, let me draw that in another color. CMN is also an equilateral triangle. So I've got to have CM and some point N somewhere is going to make an equilateral triangle. Now, since it's an equilateral triangle, that means N is going to have to be over here or over here. It can be either one. I guess we can pick one since they didn't tell us where it is. We can maybe draw it out like this, draw it out like that, just pretend that that's equilateral. And now we have N over here. So again, we could have put N over here. Maybe I'll just draw an N prime. That one we could have done, but we just picked one. So N is over here. CMN is also an equilateral triangle. What fraction of the area of triangle ABC lies inside triangle CMN? Okay, so so they're talking about the part that is the intersection between these two equilateral triangles. That's this area here. They want to know what fraction of triangle ABC is inside here. So if this is area X and the area of the big triangle is Y, they want to know that X over Y. Okay, so let's see if we can figure that out. Now we don't have any side lengths, and since they don't give us any side lengths, we can make an assumption because they're not asking us for the actual area, they're just asking us for the ratio. So if we were to set this side length to be 1, that would be fine. And we would still get the same ratio as if we set it to 2 or 3 or any other number. So I kind of like 1, or maybe 2 is better, because if we do 2, then we can have half of it be 1. Let's do that. Let's say that this side length is 2. That makes this 1 and this 1. And that makes this square root of 3, this height, because we've got a 30, 60, 90 triangle. And we've also got another 30, 60, 90 triangle. Let's see if we can draw that. So this one here is also a 30, 60, 90 triangle. But in this case, the hypotenuse, the long length, is the square root of 3. Whereas in this bigger 30, 60, 90 triangle, it was the medium-sized leg, or the medium-sized side that was square root of 3. So in this one, it's the longer one that's square root of 3. So that makes, what does that make? This one is going to be square root of 3 over 2. This one here, because it's got to be half of the long one, so that's going to be square root 3 over 2. And then we have to multiply this side by square root of 3 to get this one. So that's going to be square root of 3 times square root of 3, which is just 3, divided by 2. So that's going to be 3 halves. That's going to be the height of this, this triangle, the shaded triangle. Okay, so we need the, let's do the shaded triangle area with S. So that's going to be the 1/2 the base times the height, 1/2 of square root 3 over 2, which is our base, times our height, which is 3 over 2, and that's going to equal 3 root 3 over 8, I guess. So that's our shaded triangle area S here. Now, let's say our original triangle, I don't like O as a variable name because it looks like 0, so let's see, we'll just call that T for triangle, the area of our big triangle, T, that's ABC. That's going to be the base, which is, or 1/2 the base is 2, times the height is square root of 3. So this 1/2 and the 2 will cancel out and we'll just get square root of 3. So now when we find the ratio of S over T, we're going to get this divided by this, and the square root of 3's are going to cancel out, and we're just going to be left with 3/8. That's all that's left. So I believe, yep, that's the answer to this one, 3/8. Now, you don't have to guess an actual number here. I did that because I knew that it would work. But if you use a variable, that's probably maybe even the better, or the more precise, or the more preferred way to do it is just call this x. But if you were to do that, you would call this x, and this would be x over 2, and you'd have root 3 over 2x here, and so on. If you were to do all that, you'd end up with an x squared here, and an x squared here, and I guess these would each be divided by 4 also, unless you called this 2x. But anyway, all that stuff would cancel out, and you'd still get the same result of 3/8. So that's another way to do it, maybe in some ways preferred. Let's take a look at this one. This one says in hexagon A, B, C, D, E, F, shown here. So A, B, C, D, E, F is a hexagon, right? Because it's got 6 sides. Adjacent sides are perpendicular. Okay, so let's draw it. Let's see, we've got A to B here, B to C here, C to D up to there, D to E, E to F. And that doesn't look very perpendicular, but it's good enough. So all of these are perpendicular, okay? All these things. And the question says, if AB is 8, so this is 8, BC is 6, that's this one, CD is 3, okay, DE is 4, and what fraction of the segment AC, oh, we got to draw the segment AC, let's do that in yellow. What fraction of this segment AC, that's from here down to here. So that's AC. What fraction of the segment AC is inside the hexagon? Okay, so there's like this point here and this point here that split up AC into 3 parts. This first part here is inside the hexagon. Then this second part is outside the hexagon. And then this third part is inside the hexagon. So they want to know what fraction of that line segment is inside the hexagon. Okay, so that's interesting. Let's see if we can figure that out. First of all, we can figure out the slope of this line, right? So we know that it goes down by 8 every time it goes over by 6. And so we can use that to figure out kind of where some of these other distances, like for example, this distance here, we can figure out based on this ratio of 8 to 6. So we can make basically a similar triangle here. We have this angle here is equal to this angle here. Those are opposite interior angles. And then we have this other angle, I'll do it in a different color. this angle here should be equal to this angle here. And of course, those are complementary angles. But basically what that means is that we can use ratios like 8 to 6. So 8 to 6 has got to be equal to 3 to x. 3 to x. Okay? So we should be able to figure out what x is from that. And then we can also figure out, well, let's see. I guess we know this distance here is going to be 4 minus x. And so we can probably figure out this height of this little triangle here based on similar triangles as well, because we're going to have the same angle there and there. So we got another similar triangle there. So they're going to have that same 8 to 6 ratio. And so, yeah, let's see. Actually, you know what? We don't even need to do all of that. Once we know this distance here, whatever fraction of 6, this distance here, that'll be the fraction of this line that is inside, or that is outside the hexagon, I should say. So the fraction inside the hexagon will be 1 minus that fraction. So, okay, so the fraction that's outside the hexagon is going to be 4 minus x over 6. That'll be the fraction of this segment that is outside the hexagon. So the fraction that's inside the hexagon will be 1 minus that. So 1 minus 4 minus x over 6. And if I put this in a common denominator of 6, that'll be 6 minus the quantity 4 minus x divided by 6. Okay, so now that can be simplified. I'll put that over here as 2 plus x. 2 plus x over 6. So I'm just going from here through to there. 2 plus x over 6. So once I get x, I'll be able to figure this out. So, okay, x is going to be, oh, this is actually pretty easy here, because 8x is equal to, oh, it's not super easy. 8x is equal to 18, right? So 8x equals 18. That means x is 9/4. Okay, so I've got 2 plus 9/4. So 2 is 8/4. If I add another 9/4, I get 17/4. So now I have 17/4 divided by 6. Have I done that right? 17/4. Let me just see if I did that right. So this is 4 minus x divided by 6. Yeah, I think that's all correct. So 17/4 divided by 6, oh, maybe just write it this way, divided by 6. That's going to be equal to 17 over 24. So 17/24 of that segment is inside the hexagon. Hopefully that made sense. I don't know if I explained it super well, but you can see maybe that, like, if you project this down onto here, there's some fraction of this line segment 6 that is in here. That's that 4 minus x over 6 is that fraction of the part that's in here. And that's the same fraction of this segment that is outside the hexagon here, right? And so 1 minus that is going to be the fraction that's inside the hexagon. Okay, hopefully that made sense. Let's go on to the next one. This one says a dartboard consists of 3 concentric circles. Okay, let's grab our circle tool. 3 concentric circles. We got a big one. And these are not going to be concentric probably, maybe. Yeah, they're not perfect, but we'll just go with it. Okay, pretend those are concentric circles. And they have radii 10, 5, and 1 respectively. Oops. So there's a radius 10. That's 10. And then there's a radius 5. And then there's a radius 1. Okay. Measured in inches. The area between the largest and the middle circles is colored green. We can do that. So we color this one green. Hopefully that shows up okay. Sometimes I don't shade things darkly enough. So that's green, and oh no, that was between the largest and the middle circles. Oh no. My bad, my bad. So this area out here is shaded green. I should have used a different color for the radius, but anyway, this area is shaded green. I could have just done 3 different color circles, huh? That would have been better. Solid circles. Okay, and the area within the the area between the middle and the smallest circles is colored yellow. I got yellow here, so we can do that. This one's yellow. And then the bullseye, the one in the middle, the smallest circle, that's all colored red. We'll just pretend this is red here, so that's something like that. That's our bullseye, okay? Just fill it in. Okay, so what's the question? It says if a thrown dart is guaranteed to hit the board, but its position on the board is uniformly random, what is the probability that it lands in a yellow portion of the board? Okay, so they want to know the probability that we're in this middle section. So that'll be the ratio of the area of that section to the area of the whole thing. So we need, let's call this, there's ring 1, and then there's ring 2, and then there's center circle, we'll call it C. So they want to know the area of, if we know the area of ring 2 divided by the whole area, yeah, maybe I shouldn't call this circle. Let's call the whole thing circle. Let's call this whole area the circle instead of just the center. So yeah, let me just say circle is the whole thing. Then I want to know this probability that it lands in the yellow, probability of yellow, is going to be equal to the ratio of ring 2 to the area of the whole circle. Okay? Because we've got darts, they're thrown randomly, they might show up anywhere. We know they always hit the board, and they're no more likely to go one position than another position. So the fraction of them that will be in this yellow region will just be the area of that region divided by the whole area, because the probability has to be 1 altogether. Okay, so we need to figure that out, and we need to express our answer as a common fraction. So what is the ring 2 area? Well, that'll be a little bit smaller than the area of this circle, right? Because it'll be the area of this middle-sized circle minus the area of the small circle. So the area of the middle side, so ring 2 area is going to be pi times 5 squared, which is the area of the medium-sized circle, minus pi times 1 squared, which is the area of the smaller circle. So that will just be 24 pi. And the area of the circle is going to be pi times 10 squared, which is just 100 pi. So now this ratio here, R2 divided by C, that's just going to be 24 pi divided by 100 pi. So that's just going to be 24 over 100, or we can divide by 4 on the top and bottom. That's 6 over 25 is our probability. All right, I hope you guys enjoyed that one. We've got 2 more problems. These are going to be the hardest ones. I hope I can figure them out. All right. In right triangle ABC, yeah, I guess I should draw this over again, right? Give us some room. So in right triangle ABC, AB is 44. Let's see, it's going to be, I need to draw this like that. Okay. AB is 44, so it's 44 all the way, that's this whole distance from A down to B. And then there's a point C, there's a point E, there's F over here, and there's, oh wait, yeah, and then there's D down here. It says AB is 44, BC is 33. Okay, I don't have enough room, but 33 is the distance, well, maybe, yeah, I'll just draw it in gold here. This distance here is 33. Okay. It says point D lies on the side BC so that BD to DC, that ratio, BD to DC is 2 to 1. Okay, so if this is X then this is 2x, for example. Is that right? BD to DC is 2 to 1, yeah. And then it says if, so I didn't draw this as nicely as they did up here, but that's okay. If vertex A is folded onto point D to create quadrilateral BCEF. Okay, so this part is no longer there. This top part is all gone because it's been folded down like this. And now we have this quadrilateral BCEF like this. What is the area of triangle CDE? Okay, so let's highlight in pink this area that they want. Oops, that's not what I wanted here. So this triangle here, they want to know the area here. Okay. Let's see if we can figure that out. So, what do we know? Well, we can figure out x here, I guess, because this is 33 is 2x plus x. So that means x is 11. So we can just set this one here to be 22. And we can set this one to be 11. And they did say it's a right triangle, so we can draw this here. And now we've got 33 along the base, and we've got 44 along the height. So hopefully you're saying, Coach Jed, that's a 3, 4, 5 triangle. So here we've got 55 as the total distance from A to C. And let's see, it says area if vertex A is folded onto point D to create quadrilateral. Okay, so we need to know this area here. So what we need now is we need to know the height of this shaded triangle. We know the base is 11. We need to know the height. So we need to know how far up this point E is. You know, if we were to drop the distance down to the base here, this height is what we need. If we had that height, it would just, the area of that shaded triangle would just be 1/2 times the base of 11 times that height, h. So how are we going to find that height? Let's see, we do have, what do we have here? So, oops. Okay, this is a really tricky one. I think we're going to need to draw a couple of additional lines here. So we're going to need a line here that is parallel to this base. Okay, and that's going to give us a similar triangle with this. Let's name this one. Maybe we can name this one M. And then we're going to need to also drop a line straight down here. Well, it's not very straight, but you get the idea. That one, let's call that one N there. So, yeah, so now we've got some similar triangles. And what we can do is we can say that triangle AME is similar to triangle ABC. So triangle AME is similar to triangle ABC, which was our original right triangle in the 3, 4, 5 ratios. And then another thing that we have is that AM is 4/3 of ME because of this ratio 3, 4, 5. If we call this X, for example, here, then this will be 4x over 3, 4/3 of x. En, which is this height, that's our height that we need to figure out. That's going to be 44 minus that 4/3 of x, right? Because this total height is 44. We subtract the 4/3 of x. So height, h, is equal to 44 minus 4/3 of x. So once we get that, h, we'll be able to plug that into our area of the shaded triangle formula. in order to get our answer. So we just need to, now we just need to figure out what x is. If we can figure out what this x here is, m to e, we'll be well on our way. So how are we going to do that? I think what we need to do is we need to use the Pythagorean theorem on a couple of right triangles. So we've got a right triangle here. This distance here is going to be what? So that's going to be, well, let's see. So we have x, well, yeah, so x, so let's write the equation for this one. This will be x squared plus 4/3 x, 4/3 x squared. That's going to be equal to this distance squared. So what is that distance? Well, let's see, we don't know yet. We know the total distance is 55. So let's see what we can do. So we could make another right triangle. Well, okay, so yeah, what we know also is that this triangle was folded down from here. So this distance AE, let's call it y. Distance AE is y. That means this distance from E to D is also y because it was a folded down version. So we have AE, sorry, I'm getting a little cluttered here, is equal to ED. Okay, so we can form another Pythagorean formula down here. So let's call this y squared, right? That's this distance here. And then we have y also here. So we can set this plus this squared equal to this squared. So y squared is equal to these two legs squared, square root of those. Or y squared is this leg squared plus this leg squared, but it's also this leg squared plus this leg squared, en and nd. So let's do that. So nd, nd, well, what is nd? That'll be, let's see, 22 was from B all the way to D, right? So we don't know where n is, but we know that this nc has got to have that same 3:4 ratio with our height. So that means NC, I'll just write it in here, NC distance is going to have to equal the height times 3/4. So it'll be 3h over 4. That wasn't very good. 3h over 4, I think. That's NC. All right. And then ND will be that minus this DC of 11, right? So, okay, so, so let's see. Height is 44 minus 4/3 x. So we have, let's see, we have y squared also being equal to 3/4 of the height minus 11. So 3/4 of the height minus 11 squared plus the height squared. Okay. And we can plug in, for the height, we can plug in this. So I'm going to make some room. I think we've got the equations that we need now. We don't need the figure anymore, but we're going to need some more room to solve this. So let me erase all this stuff. I think we've got the equations we needed. Hopefully I didn't erase too much. So we've got x squared plus 4/3 of x, quantity squared, is equal to y squared, which is equal to 3/4 of h. and h is this. So 3/4 of h will be 33 minus x. So 33 minus x. Minus 11. Okay, so minus 11 quantity squared plus h squared. So plus, and I don't want h to be in there. I'm going to replace it with this x here. So plus 44 minus 4/3 x squared. Okay. So now I can probably solve this for x because it's going to be a quadratic. So let's give that a shot. All right, so this is going to be x squared plus 16/9 x squared. 16/9 x squared equal to, all right, this is 22 minus x squared. So we have 22 squared minus 44x. Oops, 44x. 44x plus x squared. That's this part. Plus we have, let's see, 43 minus 4/3 x squared. So this will be 44 squared. And then we'll have minus the product of these, which, well, 2 times the product of these. So this will be, let's see, that'll be 44 times 8. What's 44 times 8? 44 times 8. 2 carry the 3. That'll be 352 divided by 3. So we'll do 352 divided by 3x, and then there will be plus 16/9 x squared. So plus 16/9 x squared. Okay, I'm going to cancel out the 16/9 x squared here with the 16/9 x squared here by subtracting. I've also got an x squared on both sides that I can subtract. Now I just have 0 on this side, so maybe we're making some progress here. My equation is now linear, so that's good. I'm going to be able to solve for x. All right, so let's put everything with x on that other side. So I'm going to add 44x plus 352/3 of x. So I've got 44x plus 352/3 of x on one side. On the other side, I've got 22 squared plus 44 squared. Okay. Actually, I guess I can divide. Well, can I? Let's see. Maybe I should try to combine this. How many thirds do we have? So, was this divisible by 3, first of all? No. Let's see. Did I do something wrong? I think I'm okay. Let's see. So this is 44 thirds would be 100, or 44x would be 132 thirds of x. And if we add the 132 thirds and the 352 thirds, that'd be 484. So let's do that. Let's do 484 thirds of x. 484 thirds of x is equal to, now I've got 22 squared plus 44 squared. That should be 6 times 22 squared, or let's see, well, how many 11 squareds is it? Because I know 11 squared is 121. So I have 121 times, this will be 4 plus 16, which is 20. So that should be 121 times 20. Oh, look, this 44 and this 121 are going to cancel really nicely. Okay, so that's going to give me 4 over here. And I can multiply both sides by 3, and I get 4x is equal to 80. Is that right? No, I multiplied by 3, so it should be 60. Sorry. 4x is equal to 60, and that means that x is equal to 15. Okay, good. I probably am going to need my figure again to remind myself where x is. I think x was this distance here. And we said that this was 4/3 of x here. And what we wanted was this height here. Oh yeah, we've got our equation here. That's good. That's good. We've still got our equation, so we don't need that figure anymore. We're good. Good. So we can just plug in, now that we have x, we can plug it in and find h, and then we can plug it in and find the area. And then we're almost done. So 44 minus 4/3 of 15. H is going to be 44 minus 4/3 of 15. So that'll be 44 minus 20, which will be 24. And now we've got 1/2 of 11 times 20. So that's just 11 times 10. Or wait, let's see. Oh, 1/2 of 11 times 24. So that's just 11 times 12, which is equal to 132, if I'm not mistaken. Yes, 132. So that is the area of this triangle here. Okay, that was a tough one. I got kind of confused myself on that one. Thought we got it. All right, let's see. The last one says, what is the perimeter of a right triangle with an area of 10 centimeters squared? Okay, so we've got a right triangle. And I don't know if I'm drawing this even close to right, but I'll draw a right triangle. And it says the area is 10 centimeters squared. And the hypotenuse is 10. Okay, so the hypotenuse is 10. And that's all they give us. The area is 10 and the hypotenuse is 10, and then it's a right triangle. So we don't know this value here, and we don't know this value here. But we know if we multiply those two together and divide by 2, we'll get the area of 10. So if we say xy over 2 equals 10, we can solve for y, and we'll get y is equal to 20 divided by x. So maybe I'll just use that so that I just have one variable instead of 2. So let's go ahead and erase y. And we'll put in 20 divided by x here. And they want to know the perimeter. Well, the perimeter is going to be x plus 20 over x plus 10. So if we can figure out what x is, we'll be able to figure out what this perimeter is. And the last piece that we need to do is we need to use Pythagorean's theorem. So that says that x squared plus 20 divided by x squared is equal to 10 squared, or 100. And now we need to solve for x. I think one thing that could be useful would be to multiply this whole equation by x squared. That'll give me x to the 4th plus, and the reason I did that was to get rid of this x squared down on the bottom here, plus 20 squared is equal to 100 x squared. So this is actually a quadratic formula. I mean, it's a 4th order polynomial, right? Because we've got 4th order polynomial. But if you think of, if you make a replacement, you say z is equal to x squared, right? Then this thing can be rewritten as z squared plus 400, 20 squared is 400, equals 100z. So that is, in fact, a quadratic formula. It's quadratic in x squared, or as we're calling it here, z. And we can subtract 100z squared to get 0 on one side. So we've got z squared minus 100z plus 400 is equal to 0. And I don't think we're going to be able to factor this thing too easily. So maybe what we'll do is use the quadratic formula to solve for z. So let's do that. I'm going to make some room over here. We don't need those anymore. And let's grab ourselves a new color for fun. And we'll say z is equal to, using our quadratic formula, minus b, so that's going to be 100, because b is negative 100, so minus b is 100, plus or minus, so remember the quadratic formula is x, or in this case z, I'll just put z, whatever we're looking for, our variable, is equal to minus b plus or minus the square root of b squared minus 4ac all divided by 2a, where a, b, and c are, in this case, 1, negative 100, and 400. So we've got the square root of 100 squared minus 4 times 400, which is 1600, all divided by 2. Okay, and then this is going to be z. We're still going to have to square it to get x. And then we're going to have to take x plus 20 over x plus 10 to get our perimeter. So let's see if we can simplify this. 100 wait a minute, this is not good. What did I do wrong? Because this is going to give me a negative. I must have done something wrong here. Okay. Minus b squared. Oh, b was 100, so, oh yeah, no, that's fine. 100 squared, that's going to, yeah, that's still going to be positive. My bad. Okay, so we can divide, we can take 10 out of this square root, I guess. So this is, well, and I can also divide by 2, right? So this is 50 plus or minus, I'm going to take 10 out, but I'm dividing by 2, so I'll say 5 times the square root of, now this is just going to be 100, because when I took 10 out, I was really taking 100 out of this. So 100 minus 16. 100 minus 16 is 84, right? So this is the square root of, we just put that in there instead. Square root of 84. Okay, so this is z squared. And, I'm sorry, this is z. X is going to be this thing squared. Okay, so let's see. Now, it turns out that the other one of these is going to be x of the plus and the minus, and the other is going to be 20 minus x. Well, yeah, one of these squared is going to be x, and the other one squared is going to be 20. I said 20 minus, but I meant 20 divided by x. So it doesn't matter which one we pick. We just have to pick one, and it'll all work out. So I'm going to just do the plus. So 50 plus 5 root 84. That's z. And I'm going to square that thing. So this thing squared to give me x. So let's see, 84, I can simplify that a little bit too, can't I? Yeah, let's make some more room. Let's make a bit of room over here. I'm just going to erase that. So I've got 50 squared plus 500, which is 2 times 50 times 5. 500 square root of 84 plus 25 times 84. Is that right? No, I was supposed to take the square root. Is that right? Because z was x squared. I'm doing this completely wrong. Okay. Ooh, good thing I caught that. Let's see. Yeah, because we said, I got mixed up there. We said that z was equal to x squared, and it was also equal to 50 plus 5 square root of 84. So yeah, I don't want to be squaring this thing. I want to be taking the square root of this thing to get to x, right? Okay, so this is x, square root of 50 plus 5 square root of 84. And I think I can take something out of that, right? So 84 is actually, let's see, it can be divisible by 4. That's going to be 41. 1 second. you know what? I think I've been doing this completely wrong. I've been doing it a much harder way than what it needs to be. There's a little trick to this problem. So let me write this out here. We had 1/2 the base times the height was equal to 10, right? And we also had that the base squared plus the height squared was equal to 10 squared. And I think what I want to do is I want to combine these two equations so that I get a perfect square over here. And in order to do that, I need what I would like to end up with is b plus h squared, which will be b squared plus h squared plus 2bh. 2bh is 4 times this. Is that right? So if I add 4 times this equation onto this equation, I'll get this on this side, and then that will equal 100 plus 40 on this side, 140. That's going to be a lot better, I think. So, because that base plus height is actually a part of my perimeter, right? This is base and height. So really all I need, well, I can take the square root of both sides and I get that base plus height is equal to the square root of 140. And I can take 4 out of that. That becomes 2 times the square root of, see, this divided by 4 will be 35. So 2 root 35 is base plus height. And the perimeter is just going to be that thing plus 10. So that was a whole lot easier than what I was trying to do. So yeah, sometimes I'm sure I would have eventually gotten to that answer with that other really complicated way of going about it, but as you were seeing, it was becoming very messy. And sometimes you just have to find a trick, and I wasn't spotting that at first, but yeah, our final answer, now that we got this as the base plus the height, is just 10 plus 2 root 35. So sorry for my lack of spotting that at the beginning, but hopefully that's instructive, that if something seems really difficult, there's probably an easier way to go about it. So anyway, thanks to everybody for staying till the end, and I wish you all the very best on the school competition tomorrow. I'm sure you're probably not watching this because you're probably sleeping, getting a good night's rest in preparation for the school competition. So anyway, have a great holiday afterwards, and we'll see you guys tomorrow.